Good afternoon, everyone. I'm Ira Haraldsen, and I will moderate today the 7th edition of Brain Matters, which is called today, Can Digital Twins and Their Synthetic Data Contribute to a More Responsible Medical Research? Today's webinar features researchers are Huifang Wang, Ramesh Upreti, Bertrand Thirion, and Daniel Irabien Peniche. Thank you so much for participating. Each speaker will have a 10-minute session. Feel free as an audience to write your questions in the Q&A section, and we will answer your questions at the end of the webinar. Please mention the name of the speakers on your question. Please note that the chat won't be read, only the Q&A session. I will start now first with an introduction to today's issue theme. And as some of you know, I am the head of the Cognitive Health Research Group at the Division of Clinical Neuroscience at Oslo University Hospital in Norway. I'm coordinating the European large-scale project AI Mind, which is a predictive AI-based project, and I'm a partner in the EBRAINS Health and Health Data Cloud projects. Today, I was concerned, as often, about how digital twins or virtual twins or hybrids, we will go into that, will affect our medical research. And if that is really possible, we will see and we will discuss with you a little bit. It starts already usually with problems of definitions and different use of vocabulary. Some people are talking about digital twins, but are in fact referring to simulation possibilities. Others would then call a virtual twin and mix it up with a virtual model. And then the new term in AI would be the hybrid twins, and that is almost unknown in medicine so far. We will also discuss some challenges and opportunities, and it will lead you directly back why the speakers were chosen. So one more time, you see here in a very often cited publication, here are already the mixed terms. It is called multi-scale biological data background. It is then referred to a digital twin, but again, it is then already mentioned, in fact, here potentially a hybrid, because there are expressions like data integration and analysis, or modeling and silico simulation possibilities. To understand each other today a little bit better, I would like to define a digital twin as a so-called virtual model, and it reflects just correctly an duplication of a real physical object. That is what AI usually use. It needs very often big data, and it is exclusively predictive, meaning in mathematics associated to correlations. A virtual twin is something which is different. It simulates a complex environment, and it is not only a product copy, but it is also thought to give information about hypothesis-driven manipulations of different objects in a simulation virtual model way. It would give you then a hypothesis-driven approach to manipulate reality in a sense. A hybrid would then be to combine these two technologies, as we, for example, in eBrain Health, are planning in merging the virtual brain with AI mind, and then having the advantage of both systems being predictive, using simulation, and then modulate the impact on future predictive power. Opportunities seems to be obvious. It will accelerate medical diagnostics, and it will also increase intervention possibilities. It is the only way to personalize our healthcare. And it will then also be maybe able to attract more medical doctors to the AI world. And it would potentially also be able, such hybrids, to improve the healthcare or the healthcare professional AI expert in relationship, because today there are, in fact, quite a lot of misunderstandings. Challenges so far as we see today is the problem of synthesizing. It is a problem of GDPR compliance. There is no doubt the danger of data manipulation, not always in a naive meaning, but maybe also intention-directed manipulation. A very basic challenge is, in fact, that most of the medical professionals today lack the proper mathematical understanding to know something about limitations and uncertainties of our models. And it could, in a negative way, increase the gap between what is possible in clinical research and basic science and what is really done in clinical reality at our hospitals. And we have, of course, to ask ourselves, is every model development really an advantage, or are we really meeting our users' needs? And the user needs is, of course, last not least in medicine, the patient. And another very big challenge is the data quality. You know that maybe better than me that all nations are sitting on tremendous amounts of data, but they are of less quality than needed for such modeling. This was shortly my introduction. And now our first speaker is coming, and Huifang Wang will tell us a little bit why AI and simulation in combination as a hybrid might help us a little bit of the challenges. And Huifang is my very dearly colleague from Marseille University. She is working together with Victor Yesa, and she will very much be involved with all her knowledge in our future hybrid development between the virtual brain and AI mind. Thank you so much. The floor is yours.
And how hybrid thinking can help. And first, we want to see what is like AI and simulation are not enough for what, and hybrid thinking can help for what. So today's topic, I will talk about application in the neurology and how it helps for the diagnosis, treatment, and the prognosis for the neural brain disorders. Before I dig into why and how question, we want to know what is AI simulation and hybrid thinking we really mean here. The AI is use computer science and data to solve the problem in machines, and the machine learning is a subset of AI, and it can learn and adapt by themselves. And then the deep learning is artificial neural networks. So most application today for the neurology is focused on the machine learning and deep learning. So now I give one examples for AI's application in epilepsy. This is a nice leading word from UCL, and they put the structural data to the deep learning network, try to identify the lesion, the focal cortical dysplasia. It is for the seizure-free patient, they got the sensitivity of 85%. And so we can see from these examples, what is advantage of this AI. It can identify the data feature, can identify the patterns, and can save the clinician's time, sometimes can reduce the human errors. But why we say that they are not enough? Because they are black box for us. We cannot know what is inside it is, what is the mechanism it is. It cannot gain our knowledge. It can, in general case, it cannot generate new data for a new scenario. Who can do this? It's computational models. This is what we mean simulation. This is just a bunch of the mathematical equations works on the brain node to can simulate the brain activities. So here is one example. So we build for the whole brain modeling, use epileptor to simulate the patient's, epilepsy patient's brain activities. You can see it can very real, looks like real, but it cannot really help for the diagnosis and the treatment itself. How? So we need to combine AI technique and with personalized brain modeling. This is what we call hybrid thinking here. We need to build the personalized modeling, which we can also call the digital twins. It's for the epilepsy examples, we call it virtual epilepsy patient. From this patient, the TI define these models working space, and the diffusion MI can get the connectome of this patient. We use machine learning method to dig in this functional connectivity, this patient. We can identify what is epileptogenic network for this patient, which we call its diagnosis. And then further, we can do the virtual surgery, which we call its treatment. So the VEP is workflow, which can use personalized whole brain modeling and machine learning method to do the treatment and the diagnosis for epilepsy patient. So I just dig in for this patient, epilepsy patient. We use this patient anatomical information from TI, MRI, and the diffusion MRI. We build this whole brain network modeling, and then from this seizure, you can see SEEG recordings in the bottom for this patient. Use the machine learning method, we can know the parameters for this patient. We can identify the 3 brain regions we list here, and we highlight in red and yellow in these slides. And for this patient, clinical start with the yellow part as a clinical hypothesis. They did the surgery. After the surgery, the patient improved a bit, but she still cannot get the seizure free. So clinician comes to us, and we did the VEP, and we found out additional brain regions in red, and the clinician, according to this result, to did the second surgery for this patient. And for now, the patient is seizure-free for 1 year. So we always need to evaluate our models. So we use our result to compare with clinical hypotheses and also with post-operated MRI, and after the surgery, we see how to evaluate it. This is one result for the evaluation to compare with the surgery. And we can see in the middle part, the VEP performed for the seizure-free patient in green. There is only 1 patient. We found the additional 2 brain regions outside of the resection. But for the seizure not free patient, most patient, we found additional brain regions should be removed. This statistical result is very good, but we always warn us. We got this very nice result, partially also due to a very large resection for the real patient in the real world. So also another function for the virtual surgery, we said like the digital twins can simulate the brain activities in the different situations. So if you give me hypothesis that we want to remove which brain regions, we can do the simulation. So which is called the virtual surgery, can really guide the real surgery, how it looks like. So now we go to this take-home message slide. We use like, we mentioned about hybrid thinking and these digital twins. It combines personalized brain models and with machine learning method, and which can help in the real clinical world for diagnosis, treatment, and prognosis for the epilepsy, and also for Parkinson and Alzheimer's disease or other brain disorders. I use this last slide to thank you, and also our great VEP team to make this work really works. So most of our work you also can find in the EBRAINS. Thank you.
Thank you so much, Huifang.
Yes, I will start sharing now.
Yes, if you could stop sharing.
Yeah, or maybe some people can jump up me. I think I just don't know how to, okay, stop sharing.
So the next speaker will be Ramesh Upreti. Ramesh is working in our research group at Oslo University Hospital. And if you remember from the beginning when I introduced, one of the challenges is in AI, that AI in medicine usually needs or always needs real biological data, but you rarely have access to so big data that you really are able to predict correctly. And some of us hope that synthesizing may help, and Ramesh will introduce us to some of the challenges of synthesizing.
Thank you, Ira, for the introductions and having me in these webinars. I'm working as a research assistant in Oslo University Hospital, mainly responsible in two of the projects, EU recent projects, AI Mind and eBrain Health. Today, I'm going to present about the challenges of synthesizing neurological data. Before we directly jump into what are the challenges of synthesizing the neurological data, let's first understand how it's different the real and synthetic data. To collect the real data, we need participants, we need medical equipment, we need the medical or healthcare persons so that we can collect the real data. But synthetic data is a big difference. We do not need any participants, we do not need any kind of medical devices, neither we need any healthcare persons. What we all need is the data that is collected from the participants, which fits to some kinds of AI or deep learning models where the model can launch the patterns, structures, correlations, statistical properties of the real data. And based on that, it can generate the synthetic data, which looks like realistic in terms of the properties. So today I'm mostly going to talk about the challenges related with the AI-based generative models. So let's first understand what are the different kinds of models that's most commonly used in nowadays. So one of the model that we can use for generating synthetic data is autoencoder models. And the improved version of the autoencoder model is also, there is another variant called variational autoencoder models. And then we have a generative adversarial network, in short it's called a CAN, and recent innovations or diffusion-based models, which are getting quite popular in nowadays in different applications. So let's come to the challenges. So we can divide the challenges of synthesizing neurological data into basically 4 different parts. One we call pre-training sessions, and during the training parts, and a post-training, which we can also call during the validations times, and then at the time of real use. So let's go through one by one. Of pre-training channel, the challenges related with pre-training is also, we can also call it the challenges related with the data preparations. Normally, different kinds of research has shown that there is differences in the patterns of neurological patterns based on the different groups or the variations. For example, it could be like the age, gender, or class level, or geographical regions. Data has different kinds of patterns. So to use our AI-based generative models, it is very important to have a good amount of data from different variations and different groups, so that AI model can only generate the data that belongs to the different variations. And at the same time, it is very important that the data that we used for training the AI model needs to be very good in terms of quality, so that it will be not affected by the bad quality in the generations process. Often, this we can verify by doing different kinds of solutions. For example, we can do a bias checks on the data that we're going to use for the trainings, so that we can verify that it has a well represented from different groups of the data. And then if we want that there is some kind of outlier situations and that needs to be represented in the synthetic process, we can also use some augmentations techniques for that kind of outliers data, so that that kind of data is also represented well in the generations process. And there is no any standard model that can generate every types of synthetic data. So we should have to be very careful on selecting the model structures based on the types of data that we can use for synthetic process. Let's come to the training, the challenges related with the trainings. Training our generative model is very challenging as compared to the supervised classifier and regressions models. One of the most common challenges that faced by the generative model is the conditions of mode collapse, where the models can only generate one particular kind of data and fails to generate in a more generalized form. So fails to generate the different kinds of patterns of data that exist in the training samples. As the biology is very complex, it's quite difficult for models to generate the neural signals with different kind of patterns, which leads to situations of non-convergence and highly unstable models during the training times. So that kind of situations is highly faced during the training times, and normally we can mitigate these kinds of challenges by using the wise selections of loss functions. We could also come across with combining the different kinds of loss functions together. And then we can also use the techniques of normalizations that could help to handle the invariations of the data. Similarly, we cannot avoid the fact that the generative models normally requires large number of iterations in the training, because it needs to be well generalized that it can represents the training data, so that the model can learn the different kinds of structures, patterns, and correlations. So that for that we need to train. Normally, the generative models is required to train for a large number of training iterations times, which leads to situations that it becomes very expensive in terms of training time, cost, and energy, which is very important. We cannot deny this kind of facts. To solve these kinds of problem, also we could think about different kinds of model architectures that could help, and also use different kinds of tricks. For example, using a distributed training or training under a half precision situations. That kind of solutions could help to somehow reduce the training times and that kind of situations. Now comes to the validations challenges, which is one of the most difficult or the most important challenges of the synthesizing process. It is quite impossible for humans to validate the synthetic data generated by the models because the synthetic data will be on a large number of volumes. So it's not possible for human beings to manually validate each samples. So in that case, we need to use different kinds of evaluation metrics, which can basically tell us two important things. One is a fidelity, which is related to the quality or the accuracy of the data, to verify that the samples generated by the generative model is very good. If it's like image-related data, it should be verified that the images are of high quality and it does not have any kind of problems on some part of it. For example, if it's related with EEG data, the validation matrix should tell us that the generated EEG samples are noise-free, or it should not have any problems on any parts. So that's very difficult for any kinds of validation matrix. Another important thing is equally important to verify the diversity, means the different variations, whether the synthetic model or the generative models is able to generate the different variations of the data that exist in the training sample or not. Verifying all these things is very difficult and time-consuming process. So to overcome these challenges, the good way is not to rely on only one evaluation matrix. We could use like different kinds of evaluations matrix as a pipelines, and then if we pass it through the different methods, then we could come up with better solutions. Last but not the least, the challenges related with at the time of real use, as the neurological data is very sensitive healthcare data. So to use the synthetic data in a real case scenario, it should have to be compliance with GDPR rules, and then it should make sure that it should not violate any privacy information. It should not be an exact copy of the training data. So these kind of things needs to be verified, which is a very challenging thing. And as the synthesizing data is in high, so there might be a high possibility that EU even comes up with strong rules when it comes to synthesizing critical healthcare data. And at the same time, to use the synthetic data in a real scenario, like healthcare persons are skeptical about the quality of the data. So convincing and then showing the importance of synthetic data is also a challenging part. So our take-home message is generating synthetic data has a lot of potential as long as the process is implemented correctly. That's all.
Thank you so much, Ramesh. That was very nice. And we go now over to our next speaker, Bertrand. Bertrand Thirion is maybe known for several of you. He has a long life researcher career, worked on statistical biomodeling. Bertrand is as well in the eBrain Health project deeply involved, and he will now give a talk about concrete synthesizing data from the literature. Thank you, Bertrand.
Thank you for the introduction and for the invitation. So yeah, I would like to share today some recent work that we've been doing on synthesizing brain imagings from the neuroscientific literature. So the motivation for that work is that currently most neuroscientific results are stored in publications. And this is great, but this is text, and this cannot be directly used to inform data analysis, and especially signal analysis or image analysis. So the community has to face many questions, like how do we accumulate knowledge from data? How do we identify contradictions to move forward in the field? You need currently you need to read the PDF and understand, figure out if what's in there. And so at the end, the fact that the information is not directly actionable, I think it fuels the reproducibility crisis of the field, because it makes it hard to accumulate information and turn it into knowledge. So if the solution is to rely on publications, so let's try to generate images from publications. So the community does something like that when people do meta-analysis, so coordinate-based meta-analysis, which means that from each publication in the field, they would extract coordinate tables that represent locations, and then they put a Gaussian kernel in each location in the volume, the brain MNI space, and at the end, for each publication, you can end up having an image like the one on the right side that provides the location of the peaks in the image. And for instance, the Neuroscience website is built based on this principle. What we propose today is to go a bit further and to say, rather than just putting Gaussians on locations, we can do better. We can try and reconstruct the image. Why? Well, because just putting Gaussian kernels on the reported locations is limited. It's only a non-negative, it provides a non-negative map and a very sparse map. And we probably can do better than that by learning to reconstruct images. So just take real images, extract the peaks, as would do essentially a neuroscientific publication. So at the end, you obtain locations, the peaks of the input maps, and then from that try to reconstruct the input. And you can use, for instance, a set transformer that at the end reconstruct the image, or at least a low dimensional representation of the image, the so-called DFUMO representation. So what we're going to do is to try to learn to reconstruct images from the extracted peaks, and then you can take any neuroscientific publication, and using the set transformer, you can essentially reconstruct a brain image from that publication. On the other hand, you can take the text of the neuroscientific publication, in particular the cognitive neuroscience topics that are in the text, and then you can, for instance, extract them with a TF-IDF transform and use these to label each image with cognitive labels. And then you can take the reconstructed neuroscientific publication and the labels to train a decoder to classify which are the relevant cognitive terms associated with any image, okay? And then if you want to assess the quality of this technique, so what we have done was to take a comprehensive image data set and take each image and then decode it from the model that we had trained on the literature. So now we try to decode to identify the labels of real images based on a model purely trained on the literature. Okay, so to study if this works, we first assessed whether our set transformer technique that we call peaks to image is able to accurately reconstruct images. And indeed it does. We compared it to different alternatives, and we saw that overall it is competitive in terms of brain maps reconstruction with respect to other alternatives. And we can then actually generate brain images associated with different terms, just all the terms occurring in the literature, like obtain a brain map for belief, anxiety, etc. So I just propose a few of them in this image, and you can see that essentially based on the literature and the peaks to image reconstruction, we've been able to build images that correspond to frequent cognitive terms. Now, we need to evaluate if this works. So to do that, we have taken the NeuroVault collection that contains 50,000 images with relatively with user-provided annotations, which are quite arbitrary. And so we have tried to decode about 100 terms. It's the largest decoding experiment ever, because it uses all essentially all publicly available data. And we obtained relatively good scores, so an AUC larger than 0.5 in most of the terms. So it's a bit messy, this number of terms that are decoded. So we have grouped them by category, and we see that in most category we do a good job in terms of getting a high AUC, so a good classification, which is a pure generalization from the literature to the NeuroVolt collection. For instance, for learning and memory, we are able to successfully decode 13 terms among the 16 in this category. And actually, when we do that, we do better than alternative techniques that are used by other teams. So we have gains in AUC, so in prediction accuracy, and these gains are statistically significant across all the terms that are tested. We can also compare the fact that we decode from the literature, which is pure generalization, to just trying to decode from the NeuroVolt collection itself by doing cross-validation. And of course, for the terms that are on the training set, NeuroVolt, training directly on the NeuroVolt collection will do a bit better. But we can also predict more accurately terms that are not present on the training set. So with the literature, we can really learn to map, to decode any concept which was not possible previously. So we provide a better guess when no training data are available in the current open data collections. So to conclude, we have shown that learning to generate images is more powerful than using traditional special kernels to represent images from the literature. We can even do zero-shot learning with this approach by learning a model from the literature and directly applying it on a public data collection. We are still improving this, and for instance, we are wondering whether we can reconstruct images using resting state data, which would make the model even more compelling. And we are also working on the textual representation of neuroimaging publications. Here we use a TF-IDF, but it's obviously a limited representation, and we can probably do better. So far, this work has been submitted to a conference. And finally, I would like to thank you for your attention and thank my colleagues who did that work, so Raphaël Medek, Demian Wasserman, and Jérôme Deques.
Thank you so much.
I'm stopping here.
Thank you so much, Bertrand. This is really very interesting, and I'm looking forward to the discussion at the end. But before that, we are moving on to David, Irabien, Peniche, and Daniel will introduce us into the ethical, humanistic challenges of our approaches. Thank you so much.
Thank you, Ira. So, Mike, thank you for the opportunity to talk to all of you. I am working with a human-computer interaction group at Tallinn University, and I would like to basically introduce the potential that user-centered approaches and human-computer interaction can bring to improve our experience and our understanding and the potential of digital twins and synthetic data for the future of clinical medicine. So the big question is like how to develop these intelligent technologies that are effective, trust, and used, because people will always feel a certain need, there is a risk of people feeling certain uncertainty about how synthetic data is accurate, how effective it is. And a second question, and a very important question that we would like to bring here is, how can we develop technologies that are socially responsible and aligned with justice and fairness? We believe that this can be done, and there is a lot of potential from collaboration between the highly methodical and more statistically based approaches of medical clinician of research with more humanistic and qualitative methods. So I would like to introduce a bit for the concept of the user-centered approach. And I would like to start with this quote I love, which is, I suggest that the design of technology for healthcare should start with a question, how do we support clinical practice? Which requires that we understand more about the realities of that practice. This comes from a beautiful paper from Geraldine Fitzpatrick about understanding the role of paper health records in practice. Before she was working on HCI, she was a nurse, and she brought this experience to how we can not only understand, but make these technologies more effective. In this case, it will be how we make this synthetic data more effective for researchers and therefore more trustworthy for the final users, which are the patients and their carers. So what's user-centered design? It simply put, is a mixture of investigative methods and tools and generative ones. So on one hand, we understand and we explore and we try to really bring the experiences and knowledge and processes of the people who are involved in the systems with opportunities to develop and imagine futures and potential applications for how to apply, how to solve their problems, how to develop these technologies. It has a long history, and we use a combination of approaches. For the clarity of this presentation, I'm using user-centered design, but this is a big umbrella, and there are other approaches we will be using. And a secondary goal that we want to propose is that it helps to foster the adoption of these technologies. It supports the diffusion of this innovation. Digital twins was originally presented in 2002, as far as I know, and it's been just recently that this has taken this explosion because a combination of a structural and also professional practices that we have the technology and we have the opportunity to use it. But without understanding the needs of users, we cannot address their concerns and their requirements. And Velio has a paper identifying three key factors for adopting, which is benefit, reliability, and validity. And for synthetic data and digital twins to be adopted, they need to be clearly, the benefit has to be clearly stated, the reliability has to be well understood and well supported, and the validity has to be trustworthy. So how she approached this was by making a combination of interviews with different stakeholders to try to identify the roles and their needs. And this is one of the methods that we use. We use in-depth interviews. We use contextual inquiry, where we follow people and try to understand their things. We try to place ourselves in the role of researchers and stuff. So by bringing this, we can identify the different profiles and we can identify the opportunities. Now, this talk is informed by my work and the work of my team in the AMIN project. We believe that it has shown a potential for these methods in developing innovative tools for healthcare. Because the main problem that we can help support is the complexity and multiple stakeholders involved. These methods can help them communicate. I'm going to move a bit further because I want to identify these concerns. The concern with synthetic data is reliability and accuracy. How do we trust the data? How do we keep the connection between the physical and the synthetic? How do we integrate these technologies into our practice? And how do we ensure data security and privacy? It has been mentioned a lot about GDPR, and one of the main potentials of synthetic data is it seems more robust about privacy. We know anonymization is never fully complete, especially with this sensitive data. And by having synthetic data, one of the main advantages it can be is the use in hackathons for students. It makes the data more accessible. And I want to identify two challenges that come from the human-computer interaction community in a very beautiful paper from Vani Onpa about digital twins. The ontological challenge, that the digital is always an a reduced projection of the material original. It's never the thing, but it's very close to the thing. The closer the better. But we need to understand that as a challenge. and the visibility challenge. Who we collect, which kind of data, and which kind of data we don't, make some things visible and some things invisible. And this is particularly sensitive to power and structural issues. So we believe that one of the main contributions we can bring is a question and a way to explore how this will give rise to new power relationships between stakeholders, who is going to have a voice in it, and to allow other communities to have a voice. So I'm going to, based on Vanini OPA, there are basically 4 dimensions of digital twins that we need to, these are data-driven systems. They have a relationship with the real world. They have a dynamic interaction between the physical and the digital. They create value, and this is important about this data. Data is hard and data is expensive, and health data is extremely protected, so it's not accessible. But by making it more accessible, we can really further medical research. We can really further our understanding. And we need to understand all the places where value is created and what are the possibilities and potentials. And this is a very good place where human-computer interaction and user-centered design can expand the perspectives that we have. And digital twins and synthetic data are not complete copies. So some of the examples, for example, for making the systems more robust in the case of data-driven systems, we can map better the variables, we can understand better the communities, we can kind of bring a more nuanced approach of who are the different groups and different voices we need to bring into the models. We can explore how useful they are, and we can allow these people to express their concerns and to be taken into account. This is not to move the role of the researcher and the healthcare practitioner, but to inform them better of the world they are modeling and the people they are working with. And because sometimes we always come from the perspective of our job, and we need to expand it. For the second is the opportunity to understand the context and the critical interactions, what we call the located accountabilities, which is where is this system going to incite and how it's changing the life and the daily routine of the people. Having this data at the end of the day may not affect some of the people that are working, but it may affect them in the relationship with their own health and their own understanding. And this is something where visibility and explainability can work a lot, and we can help explore how to better communicate these relationships and to understand how to better work with these decisions. The dynamic interaction between the physical and the digital, this is where mapping these interactions can make the system, again, more transparent and robust by basically explaining how the system is built and the system explaining its power and at the same time its restrictions. The value-centered design, which is part of the umbrella, can explore novel or not evident perspectives, like the politics and the power relationship that affect the systems. One of the main concerns we have in the AMI project is, and one of the hopes synthetic data can bring, is to ensure that all the population is benefited from these systems, not only those who are more fortunate or with more privilege, that they can participate and engage with the creation of novel technologies for their healthcare. So this is a place where we are very optimistic and we are very excited about the potential for user-centric design. And finally, the question is, we can widen and integrate more voices. By bringing these user inquiry methods, we can really expand the voices and the perspectives that inform how we build these models. This was just a very brief presentation because I only have 10 minutes and I'm 20 seconds about to finish. But I'm hoping to hear so many questions and to continue working with anybody who's interested on these topics, because we believe there is a strong potential for bringing all these methods to us. And I'm going to stop sharing.
Thank you so much, Daniel. It's a very nice last talk, because you give us some hope that synthesizing is in fact helping us with some of the difficult issues of representativeness of cohorts, and that the more we can learn by EBRAINS, for example, sharing data, we would be able to synthesize a more multicultural environment, in a sense. In the audience, has some of the questions are going just into that direction, and I would like to start. A question is coming for Ramesh, and here the audience is asking you if synthetic models could in fact generate completely new biomarkers.
Yes, this is very interesting questions, and often people think that the synthesizing process can generate any kinds of data and can even completely replace the real data, but I think that's not the true. The synthetic data is the generations of the synthetic data. It's completely dependent on which data it is trained. So if and then based on that training, it can generate the biomarkers, different variations of the biomarkers that exist on the training sets. Because of some random process, it might generate some little bit different kinds of biomarkers, but it is not likely that it will generate completely new biomarkers during the generations of the generative models. So it heavily depends on the data that is used for the training the generative models.
Yes, and into the same direction, Huifang, is the audience wondering what is the role of synthetic data in the virtual epileptic patient in your model? Could you explain one more time? Because simulated data is in fact a kind of synthetic data.
Yes, and if we define, like, I think there is mainly two main rules for the synthetic data. It's independent, as I would like to say, two independent rules for the synthetic data, how to involve our studies and also maybe to generalize the most general cases. The first is like we always use synthetic data to compare with the real data. And this is also very important for us to write an objective function for the machine learning method. So they can train this machine learning method to find the best parameters for the models as well. So this is like synthetic data can help us to really build these digital twins. Then the second part of the rules of the synthetic data is in the evaluation rules. So when we build the pipeline, the algorithm, we first to try on the synthetic data, because in some real world, we don't know the ground truth. But in the synthetic data, the world, we set the parameters, we know the ground truth, so we can to evaluate the method, it works valid or not. So we also published now it's trying to generate like the cohort, the data set, to publish it in the for the committee that people can use it to also to test their own algorithm, because there we know the ground truth. So this is mainly two roles for building the models and then to evaluate the algorithms. Thank you.
Yes, I think you are very right. And what you are mentioning is going also, is reflecting on the question to Ramesh, and it is leading to the question of to Bertrand, where the audience is wondering, is this kind of thinking in physics dimensions of creating something new and then testing what Huifang is calling the ground truth, is it really behaving as the reality? Then the question to Bertrand is, how can we ensure representativeness of the results? Are they really representative for what is really going on in the clinic?
Well, that's a hard question. And I would say humbly that our results are certainly biased by the kind of data we have access to. Actually, there are some fashions in the community, like in the publications, there are some trends. People like to nominate or to call things in a certain way, and this fluctuates over time. And when you do meta-analysis on the literature, you are essentially integrating over all these fashions and trends. It's the same thing when you have an evaluation dataset like NeuroVolt. It clearly has some biases. And what we are presenting, what I was presenting today, is certainly showing all these biases. My hope is that once we have at least a decent validation of this technique, we can then switch to reports, to case reports, like all the information that has been collected on individual patients with certain cases. At the moment, we are not even able to exploit this data. It's just, buried somewhere in big repositories, but this cannot be used to inform our data analysis. My hope is that we can use all this information that exists in case reports to build a more informed model on brain function and brain dysfunction. So knowing associations between some lesions, for instance, and some behavioral traits is really important. And so I believe that with this approach, we can really leverage these untapped resources of case reports.
Yes, and I would even go further with the other speakers that maybe these technologies and digital and virtual models would, as a hybrid, would be able then to increase variability of data and would in fact improve the criticism which is often given from clinicians to researchers, that they only describing their cohorts but not the clinical reality. And with these technologies, we are maybe as researchers for the first time in the possibility really to meet clinicians. It could be just the opposite of the fear often announced nowadays to those techniques. And a last question, Ramesh, is how do AI and synthesizing promote and help with outliers? Because outliers could also be a very important information which is often driving later hypothesis.
Yes. It is very important to be very selective on the model architectures when to taking care that outlier also be generated by the synthetic models. For example, if you talk about the generative adversarial networks, GAN-based models, it is often like that it misses the outlier kinds of data in the synthetic process. But if you use like the diffusion models, they are very good at generating the outliers kinds of data as well. So we need to be very selective on the types of the model architectures so that it can handle that kind of situations as well. So if we choose the models correctly, then that kind of situations also be nicely handled. For example, if we even like the variational autoencoder is also good for generating the outliers models as compared to the GANs. So if we choose that there is some outlier situation and we do not want to miss out that, then we need to be very selective on the model architectures as well.
Yes, and just in the last minute, another interesting question is coming, which is in fact continuing into your direction, Ramesh. The audience is asking me how can we guarantee the needed expertise to deal with AI and synthesizing when building platforms. And I think this is a real challenge, because we are very quickly developing those platforms and opportunities and AI technologies, but we are maybe not actively enough communicating. And I will encourage this audience today here to join the EBRAINS community, to join our public seminars and lectures. And we plan to introduce systematically to symposia about how to build concrete such models, and coming directly in concrete collaboration with all of you. I think the only way out of this dilemma is in fact to communicate and to make it interdisciplinary, as Daniel also underlined it, transparent what we are doing and why we are doing it. Thereby, I would thank you very much for this seminar, and I hope we see you all soon again. Thank you so much. Bye-bye.